Hi, I'm Dr. Umair Munir, and today we will learn how to create building frame in SpaceClaim and how to use Ansys for analysis of building frame and how to validate the Ansys solution. Let me first explain what is a rigid plane frame. When a series of beam elements are rigidly connected to each other in such a way that the original angles made between elements at their joints remain unchanged due to the applied loads. For example, if the load is applied on this building frame and the angles do not change after the application of force, then we can call it a frame. So we now do a example from a book, a first course in the finite element method by Darrell L. Logan, 6th edition. So problem is 5.62. A two-story building frame is to be designed. Let the horizontal beams to have a 15-inch depth. This is depth. This side is depth, and it should be at least 15-inch. And the columns to have a 10-inch width. That means the width of this beam should be at least 10-inch for vertical beams. The material is to be A36 structural steel. The allowable bending in the beam is 24,000 psi. Check buckling in the columns using Euler's and Johnson's method as appropriate. The allowable deflection in the beam should not exceed 1 by 360 of each beam span. The overall sway of the frame should not exceed 0.5 inch. These are some limitations of this problem. So we will select the beams. Horizontal and diagonal beams are made of W16 into 26 beam, and the vertical beams are made of W is equal to 10 into 49-inch beams. The dimensions of these beams are given in this table, and we will use these dimensions to create our geometry. Now we go to Ansys workbench and drag static structure into project schematic. Let's go to double click the engineering data. Our material was A36 steel, and for this A36 steel the value of Young's modulus is 2.9 into 10 raised to power 7. So we will change the units into PSI into US engineering, and we see that the Young's modulus value is 2.90 into 10 raised to power 7 psi, and the Poisson ratio for A36 steel is 0.32. We change the value of Poisson ratio. Then we will close this engineering data, go to geometry, double click it. It will open up SpaceClaim to create the geometry. So first we will select the plane. We will select the plane. And then we will change the units. Go to File, SpaceClaim Options. Click Units, and then change the units from metric to imperial. Click OK. Then we will draw a construction line. Click on this button, construction line, and then click on the origin. The length of this construction line is equal to 120 feet. Press Z button to zoom in. These dimensions are taken from this figure. You can see here the first length of this beam is 10 feet, and the horizontal beam is also 10 feet, The next horizontal beam is 15 feet away. So we use these dimensions. The next length is 10 feet. We will enter a value of 120 inch. Then we draw a vertical line which is also 120 inch. Press escape. The next line is 15 feet away, and 15 feet means 180 inch. Enter this value. The next line is a vertical line which is 10 feet, 120 inch. Then click on this point, and the length of this line is 8 feet. 8 feet means 96 inch. We can confirm in the figure that it is 8 feet high, and the height of this triangle is 5 feet. Draw a horizontal line equal to 180 inch, then a vertical line which is 96 inch. Then from the center point we will take a height of 5 feet which is equal to 60 inch, and then we will join these two points. So we have drawn the building frame, its construction lines. We'll use these construction lines to draw the beams. So we go to a home view, and then now we will select a plane, XZ plane, on which we will draw the cross section of the vertical beams. So we select this plane and then we look at this plane. Now we draw the beam cross section on this origin point. So I draw a line here, construction line, and right click on this line and set it as mirror line. So the vertical beam dimensions are given in this table. Its width is 10 inch, height is depth of this beam cross section is 9.98. So I draw a solid line from this point, and length of this line is 4.99. So here it is, the line. We'll open a calculator. 9.98 divided by 2. So it is 4.99. 9.98 was depth of the beam. So now we will draw another line starting from this point, and its length is equal to 5 inches. Then a vertical line, which is the flange height. Flange height is 0.56 and web thickness is 0.34. Flange height is 0.56, enter this value, 0.56. The angle was not correct, so we'll press the escape button, Ctrl Z, and then draw this line again, 0.56. Then we draw another line, horizontal line, which is equal to the width minus the web thickness. So go to calculator, and total width is 10 minus web thickness is 0.34 divided by 2. 4.83 will be the length of this horizontal line, 4.83. Enter. Then we draw a vertical line, and its height is equal to the total depth of the beam cross section minus 2 times of flange thickness. So total height of this beam is 9.98 minus 0.56 minus 0.56. 0.56 is the beam flange thickness. So 8.86. 8.86. So now we draw a horizontal line equal to the length of 4.83 inches. Press enter. Then a vertical line having height of 0.56. Then a horizontal line to finish our sketch. Press enter. So we will trim this center line. Press trim button, just trim away, and click on this line to trim, and our sketch is now complete. We go to home view and zoom in and click on the pull button. Select this surface and then pull the surface by dragging this upward arrow, and we give it a value of 120 inch. Now we have drawn our first beam. Now we will copy this solid, and we know all the vertical beams are made of the same cross section. So I click on this solid here, click on this solid, click on this copy button, and then paste button. So it will copy and paste this beam. I need another copy, so I will click on the copy button again and then paste button. Now you can see there are 3 solids. So I uncheck 2 solids here, and I have now remaining 1 solid checked. I will move this solid to this line. So for that purpose I will click on this move button and click on this arrow, and then I will click the button, this button which is up to, and click on this line. Now you can see that this beam has been moved from this line to this construction line. Now I will I will check this solid as well and click on this solid. Now I want to move this solid to this next construction line. So for that purpose I will click on the move button, then click on this red arrow, and then click this button up to, and then I'll click on the next construction line. Now I can see the three solids. I will check this box here, and now I can see three solids, and I will then click on this pull button, click this surface and reduce its height. Now I can easily select now I can select this point and create a plane here. Now the plane has been built. I want to select this plane and press the plane view button. Select the plane and plane view. So we will create our geometry on this plane. First we will draw a construction line here, horizontal construction line. Click on the plane view button. Then I will draw a line, vertical line having length equal to 15.69 divided by 2. 15.69 divided by 2. 7.845. Draw a construction line from this center point, and its length should be 7.845. And from this center line I will draw first right click on this line and set it as mirror line, and then I will draw a solid line having width of 5.5 divided by 2. 5.5 divided by 2 is equal to 2.75. 2.75. Then a vertical line having thickness of 0.345 and web thickness is 0.25. So this thickness of flange is 0.345. Then this horizontal line length is total web width, which is 5.5, minus web thickness is 0.25 divided by 2. This is 2.625. 2.625. minimize it, and 2.625. Then I will draw a vertical line which its length is equal to total depth of the beam, which is 15.69, minus flange thickness 0.345 minus 0.345. Minimize it and then enter a value of 15 inch. Then draw a vertical line having length of 2.625. Then draw a vertical line having length of 0.345. Then join these two lines. So now the cross section of the horizontal beam is complete. Click the pull beam. Now I will select this surface and drag this arrow and give it a length of 60 inch. Now we have this beam, horizontal beam. Now we will copy this beam to other locations. For copying this beam, I will click on this solid button and then click copy and paste. Now I will move this beam to this location. For this purpose, I will click on the move button, click on this vertical arrow and then click up to and select this line. Now it is moved from this horizontal line to the upward horizontal line. Now I will create the diagonal beams. For that purpose, I will rotate this beam. First I will copy this beam, then I will rotate it. Select this beam and then copy and then paste. Now I want to move this beam. Click on this move button and click on this red arrow, then click on up to and then select this point. Now we will rotate these two beams along the line, this diagonal line. So first we need to find its angle. So we go to measure, click on measure and click this line and press control key, then click on the other line. So we can see here that the angle between these two lines is 33.69. We will use this angle to rotate this beam. Go to design button, click on the move button. First select the solid and now drag this to this point. Drag it to this point, which is the center point. Okay. Drag this to this center point. Now we will click on this blue rotation arrow and give it a value equal to 360 minus 33.69, which is equal to 326.31. So 326.31. So now our beam is in the correct direction. Now I will click on the select button, select the other beam. It is not correctly positioned. First we will position it correctly. Press on the move button and drag this to the end point. Drag it to end point. And now we will move this beam to this center point, this corner. And for this purpose I will click on this arrow and then press up to and then click on this point. It will move the beam to this edge. Now I want to rotate this beam and I will click on this rotation button, rotation arrow, and drag it. The angle will be equal to 33.69. So now our beams are in the correct angle. So we will hide these two beams for now. And now we will copy this horizontal beam to this line. We select this beam. We'll press copy button and then paste. Now select this beam and move it in the vertical direction. Press this arrow and then press up to and then select this line. Now we will pull each of the beam to its required length. For this purpose we will first uncheck the other beams. For example, I want to hide other beams, so I will uncheck these boxes. So now I will pull this beam. For this purpose I will click on the select button. I will select the surface of this beam. This surface I will select it. Then I will click on the pull button, then home button, and then I will pull this beam up to this point. And then I will again check this box and then uncheck the other box to hide the other beams. So now I will pull this beam. So I will select this cross section, select it, and then press home button, pull, then press pull button, up to button and select this point. Then I will hide this beam and check this box to show this beam. Now I will pull it by selecting this surface, zoom in, select this surface, press home button, press up to button and click this point. Now I will hide this beam and show this horizontal beam. So press home button. I will now select the surface that I want to pull. Select this surface, press home button and then press up to button and select this edge, this point. Now I will hide this beam. The reason why I am hiding these beams, if I do not hide these beams, it will make it a single body. That for now I do not want to become a single body. I will show you later that when I will show all the beams, it will become a single body. So I now want to pull the vertical beams. So I'll show the first beam and I will zoom in to select the surface and then go to the home button and I will pull it up to this point. Click this point to pull this beam up to that point. Then I will show the other vertical beam. This I will show it again, the height, and hide the other one and then zoom in to select the surface. Select this surface, press home button, press up to and click then to this point. I want to extend it. Click here to extend its length. Press home button and now I will hide it and see that if any beam which is left. So all the beams are now extended to their limits. So I will show all, check all the boxes and now our geometry is now complete. So if I want to make them a single body, I will select all these bodies and then press combine button to make them a single solid. Now we will split the beam surface. We will select this beam surface and we will split it, this surface, to apply the force. We will click on the split button and then we go to right view and zoom in and we will split this surface around this center line. So now we can see here that our beam surface is now splitted into two. Now double click on the model button. Now click on the mesh button, right click and generate the default mesh. It will take few seconds to generate the default mesh. Then we will apply fixed supports. Click on the static structure, click insert and add a fixed support. We select the surfaces. First we rotate the model and then zoom in to select the surface. Click on the face selection button, then click this face, then apply. Click static structure, right click, insert, pick support, zoom out, then zoom in to click to select this face. Select this face, then apply. Click on static structural, insert, fix support, zoom out, zoom in, then select this face and apply it. Then we will apply forces. Click right click static structural, insert, force, isometric view, zoom in to select this surface, apply the surface. We will define the force by components, and the force which is applied on this surface is equal to 150 pounds multiplied by 10 feet, that is 1500 pounds. So we will apply in the negative y direction 1500 pounds. Then we will go to static structure, right click, insert, force, select this surface, apply. We define the force by components, and this is equal to minus 4500 pounds, because we see in the problem that there is 300 pounds per feet and there are total 15 feet, so 300 multiplied by 15 is 4500 pounds. Then we will apply a horizontal force, zoom in this area, then click on the static structure, insert, force, here it is, force, and we will click on this edge and then apply. Then we will define the force by components, and it is in the negative x direction, minus 5000. Then we will zoom out, and then we will apply another force. By seeing this diagram, we have applied this 5000 force. Now we will apply this negative 10,000 pounds force in the negative x direction. We will zoom in this area, we will select this edge, and we will add another force, insert, force. The edge is already selected, and we will define this force by components, and it is in the x direction, minus 10,000. So now we will click on the solution button and right click, insert, deformation, directional deformation, and directional deformation is in the x direction. Then we will again click on solution tab, right click, insert, and another deformation, directional deformation, whose direction is, orientation is in the y axis. Then click on the solution tab, right click, insert, and stress equivalent, von Mises stress. Then we click on the solution tab again, right click, and then solve. It will take few seconds to solve, and then we will analyze our results. So zoom to fit and see the directional deformation. You can see here that maximum directional deformation is 0.49, and it is we can probe the maximum value, where it is the maximum value and where is the minimum value. So the minimum, that means minus 49.49678 inches, it's in the at the top of the frame. So we will compare it with the allowable value. Here we can see that sway in the frame is allowable up to 0.5 inch, and our Ansys has given us a value around 0.49. Now we will see in other results, and we go to equivalent stress, and we find out that maximum stress is 30,000 psi, which is at the joints. It is due to stress concentration. So we will find out the bending stress in beams. So we will probe the stress, go to probe button, and we will probe this value of stress in the beam. Bending stress is maximum in the beam is around 5,000 or somewhere around 6,000. So our allowable limit was 24,000 psi. So maximum bending stress which is found in the beams is around 7,000 or 8,000 value. So our design is safe with respect to bending stress if we ignore the stress concentration due to the sharp edges. Now we will confirm the buckling of this column. So we need to find out the critical buckling load. So we have this equation, Euler's column formula for critical load, and we know that our beam is fixed at both ends. So the value of n for this case is equal to 4. We have this buckling formula in which n is equal to 4, pi is 3.14 square, E is 2.9 into 10 raised to the power 7, and I, moment of inertia for vertical beams, is 93.4, which was already given in this table. 93.4 along this is moment of inertia along y-axis. So and the length of this column is 120. So we find out that the critical load is 7.42 into 10 raised to the power 6. This critical load is much higher than the applied load. Applied load at this beam was 4,500 pounds. So there is no chance of buckling. So our frame is safe from buckling, and the sway in the frame is also in the allowable limit, and bending stress is also in the allowable bending limit. So deflection in beam should be less than beam span divided by 360. So this beam was having maximum length equal to 180 inch. So 180 inch, if we divide it by 360, so we will get a value of 0.5 inch in the so allowable deflection was 0.5 inch in the vertical direction, but we have the limit of we have got a value of directional deformation in the y direction. The maximum deflection is 0.049, which is the vertical deformation in the beam, which is, you can see here, it is showing us a minimum value because it is directed in the negative y direction. So it is assigning it as a minimum, but we have this value 0.049. So this vertical deformation in the beam is also in the given prescribed limit. So our design is safe both in terms of stress and deformation.